Our universe is a place of incredible vastness and complexity. It stretches beyond our imagination, filled with wonders that challenge our understanding and inspire our curiosity. It's filled with stars, galaxies, and mysteries yet to be unraveled. Each star, each galaxy, is a beacon of light in the dark expanse, holding secrets of the cosmos. But how did this awe-inspiring cosmos come to be? What events led to the formation of such a magnificent and intricate universe? The prevailing scientific theory points to a singular, momentous event, the Big Bang. This theory is the cornerstone of modern cosmology, providing a framework for understanding the universe's origin. This theory suggests that our universe began from an extremely hot, dense state about 13.8 billion years ago. In an instant, it began to expand, setting the stage for everything that would follow. From this fiery origin, it expanded and cooled, giving rise to the stars, galaxies, and planets we observe today. The cooling allowed matter to coalesce, forming the first atoms, and eventually the complex structures we see. The Big Bang Theory is not just a compelling narrative, it's a scientific explanation supported by extensive research and evidence. It's supported by a wealth of observational evidence. Scientists have gathered data from telescopes and space missions, all pointing to the same conclusion. We see this evidence in the form of relics, remnants from the universe's earliest moments that still echo through the vast cosmic expanse. These relics are like ancient whispers, telling the story of the universe's birth. These relics serve as cosmic time capsules, offering invaluable insights into the conditions present during the universe's infancy. They are windows into a time long past, yet crucial for our understanding. By studying them, we can piece together the story of our universe's birth and evolution. Each piece of data is a clue, helping us to reconstruct the grand narrative of cosmic history. One of the most compelling pieces of evidence supporting the Big Bang is the existence of the cosmic microwave background radiation, often abbreviated as CMB. This radiation is a faint glow that fills the universe, a remnant of its fiery birth. This faint afterglow of the Big Bang permeates all of space. It is a snapshot of the universe as it was in its earliest moments, a time capsule from the dawn of time. It provides a snapshot of the universe as it existed a mere 380,000 years after its birth. This period, known as the recombination era, marks a significant milestone in cosmic history. Another crucial relic is the abundance of light elements like hydrogen and helium, forged in the intense heat of the Big Bang's aftermath. These elements are the building blocks of stars and galaxies. These relics and others like them are not merely curiosities. They are essential clues that help us unravel the mysteries of the early universe. Each element, each particle, tells a part of the story. They are essential clues that help us unravel the mysteries of the early universe. By analyzing these elements, scientists can infer the conditions and processes that shape the cosmos. By studying these remnants of a bygone era, we gain a deeper understanding of the fundamental forces that shaped our cosmos. Forces like gravity, electromagnetism, and nuclear interactions played pivotal roles in the universe's evolution. In doing so, we come closer to answering the profound question of our cosmic origins. The quest to understand the universe is a journey through time and space, revealing the wonders of our existence. Imagine looking up at the night sky and seeing a faint, uniform glow emanating from every direction. This glow is not something you can see with your naked eye, but it is there, permeating the cosmos. It is a relic from a time long before stars and galaxies formed, a whisper from the dawn of the universe. This glow, invisible to the naked eye, is the cosmic microwave background radiation. Discovered in the mid-20th century, it has since become one of the most important pieces of evidence for the Big Bang Theory. It is a faint echo of the Big Bang, a whisper from the universe's earliest moments. This radiation has traveled through space for over 13 billion years, carrying with it a snapshot of the universe when it was just a fraction of its current age. This radiation was released when the universe was just 380,000 years old. a time when the universe had cooled enough for atoms to form. Before this period, the universe was a hot, dense plasma of particles, but as it expanded and cooled, these particles combined to form neutral atoms, allowing light to travel freely for the first time. The CMB is often referred to as the baby picture of the universe. This analogy is apt because it provides us with a snapshot of the universe during its infancy, a time when it was just beginning to take shape. This analogy is apt because it provides us with a snapshot of the universe during its infancy. Just as a baby picture can reveal subtle details about a person's future appearance, the CMB contains a wealth of information about the early universe and its subsequent evolution. Just as a baby picture can reveal subtle details about a person's future appearance, the CMB contains a wealth of information about the early universe and its subsequent evolution. By studying the patterns and fluctuations in this ancient light, scientists can learn about the conditions that existed in the early universe and how they led to the formation of the structures we see today. By studying the subtle temperature fluctuations in the CMB, cosmologists can glean insights into the universe's age, composition, and geometry. These fluctuations, though tiny, are incredibly significant. They represent minute variations in the density of the early universe, which would eventually lead to the formation of galaxies and other large-scale structures. These temperature fluctuations, though tiny, are incredibly significant. They represent minute variations in the density of the early universe. These small differences in density were the seeds from which all the structure in the universe grew. They represent minute variations in the density of the early universe. Over billions of years, these variations would grow under the influence of gravity, eventually giving rise to the large-scale structures we see today, such as galaxies and galaxy clusters. These variations, over billions of years, would eventually give rise to the large-scale structures we see today, such as galaxies and galaxy clusters. The study of the CMB allows us to trace the history of the universe from its earliest moments to the present day. Therefore, the CMB provides us not only with a glimpse of the universe's past, but also with clues about its future evolution. By understanding the initial conditions of the universe, we can make predictions about its ultimate fate. The discovery of the CMB in 1964 was a watershed moment in cosmology. It provided compelling evidence for the Big Bang theory and revolutionized our understanding of the universe's origins. This discovery was made by accident when two radio astronomers, Arno Penzias and Robert Wilson, detected a persistent noise in their antenna that turned out to be the CMB. It provided compelling evidence for the Big Bang theory and revolutionized our understanding of the universe's origins. Before this discovery, the Big Bang theory was just one of several competing theories about the origin of the universe. The detection of the CMB provided the first direct evidence that the universe had indeed begun in a hot, dense state. Today, the CMB remains a subject of intense study. Scientists continue to analyze its subtle features, hoping to unlock even more secrets about the universe's earliest moments. With each new observation, we learn more about the fundamental nature of the cosmos. Scientists continue to analyze its subtle features, hoping to unlock even more secrets about the universe's earliest moments. The study of the CMB is a testament to human curiosity and our desire to understand the universe we inhabit. It is a journey that continues to this day, with each new discovery bringing us closer to understanding the true nature of the cosmos. In the immediate aftermath of the Big Bang, the universe was an unimaginably hot and dense inferno. Temperatures soared to billions of degrees, creating an environment so extreme that the very building blocks of matter were in a state of chaos. This was a time when the universe was a seething, roiling mass of energy and particles, a far cry from the structured cosmos we observe today. Temperatures were so extreme that even atoms couldn't exist. In this primordial soup, particles like protons, neutrons, and electrons were constantly colliding and interacting, unable to form stable structures. The energy levels were simply too high for any kind of atomic bonding to take place. As the universe expanded and cooled, however, a crucial transition occurred: the formation of the first elements. This cooling allowed particles to slow down enough to combine and form the simplest atomic nuclei. The universe was still incredibly hot, but it had reached a point where the first steps towards chemical complexity could begin. This process, known as primordial nucleosynthesis, played a pivotal role in shaping the universe's chemical makeup. During this brief but critical period, the universe underwent a transformation that would set the stage for everything that followed. The conditions were just right for nuclear reactions to occur, leading to the creation of the first elements. During this epoch, which lasted for just a few minutes, protons and neutrons, the building blocks of atomic nuclei, began to combine. These combinations were not random but followed specific pathways dictated by the laws of physics. The result was the formation of the first atomic nuclei, primarily hydrogen and helium, with trace amounts of other light elements. This fusion process, fueled by the intense heat and pressure, gave rise to the lightest elements: hydrogen, helium, and trace amounts of lithium. These elements are the most abundant in the universe and serve as the fundamental building blocks for all other elements. The creation of these light elements was a monumental step in the evolution of the cosmos. The precise abundance of these elements, predicted by the Big Bang theory, matches remarkably well with observations. This remarkable agreement between theoretical predictions and actual measurements provides strong evidence for the validity of the Big Bang model. It shows that our understanding of the early universe is based on solid scientific principles. This agreement between theory and observation is a testament to the power of the Big Bang model. It underscores the robustness of our cosmological theories and the accuracy with which they describe the universe's earliest moments. The success of the Big Bang model in predicting the abundance of light elements is one of its most compelling triumphs. It provides strong evidence that our understanding of the early universe is on the right track. The study of these primordial elements offers invaluable insights into the conditions that prevailed in the moments following the Big Bang. By examining the distribution and abundance of these elements, scientists can reconstruct the history of the universe with remarkable precision. The formation of these first elements was a critical step in the universe's evolution. It marked the beginning of a new era where the universe transitioned from a chaotic, high-energy state to a more structured and stable one. This transition set the stage for the formation of more complex structures, including stars and galaxies. It set the stage for the formation of stars, galaxies, and eventually, the planets and life itself. The light elements created during primordial nucleosynthesis served as the raw material for the first stars, which in turn produced heavier elements through nuclear fusion. This ongoing process of element formation and distribution is what drives the chemical evolution of the universe. The process of primordial nucleosynthesis essentially laid the foundation for the chemical complexity we observe in the universe today. Without this initial creation of light elements, the universe would lack the diversity of elements needed to form planets, organic molecules, and ultimately, life. The elements forged in the first few minutes after the Big Bang are the building blocks of everything we see around us. Without this initial creation of light elements, the universe would be a vastly different place, devoid of the stars, galaxies, and ultimately life as we know it. The absence of these elements would mean a universe without the complex chemistry needed to support life. It is the presence of these light elements that makes the universe a dynamic and evolving place. The study of these primordial elements therefore provides a crucial window into the universe's earliest moments and its subsequent evolution. By understanding how these elements were formed and distributed, scientists can gain deeper insights into the processes that have shaped the cosmos over billions of years. This knowledge not only helps us understand our own origins, but also the fundamental workings of the universe itself.